And you also get your 3D seismic cube dimensions. So you get the origin, the grid size, cell size, azimuth, number of cells. You can see here that the one that we're about to import is 153 million cells. And while it imports, I'll just let you know that this data is from Darlow Gold Mine in Australia, and it's a courtesy of Red 5 Limited. Okay, so here we have our seismic cube. I'll just turn on some sections, my U, V, and Z sections, and I'll also paint them by that seismic amplitude property. And this will just take a couple seconds. Okay, so now we can edit the data colors. For example, I can change the color table to seismic, or I can also make it flag like this. And I'll also change the color mapping function. I'll leave it as linear. I'll just trim it on both sides. And again, this is going to take just a couple seconds, but it shouldn't be too bad. Like that. Just a moment. Here we have it. So the same filters that you would usually use in your data colors should apply if you want to see only the high amplitude or maybe the low amplitude. That's all still the same as the usual geoscience analyst functionality. In terms of the visual parameters, you can make the sections smooth. You can move around your U, V, and Z sections. You can also create a section in like any given orientation. You can show volumes and also ISO values, which in this version have been updated to make it a little bit faster. So yeah, that's it. That's how to import and visualize your 3D segue files. And that's all part of Geoscience Analyst's like free import and visualization functionality. And on that same theme of seismic, I'll show you another new tool, and that's the seismic survey planning. So let me just go over there, here. So what I have here is a topography surface, and then I have these two surfaces, so these two structures that I want to hit with my survey. So I'll go to my panels menu, survey designer. And here we have this new option, the seismic reflection survey. So I'll just click on this one. And I'll make this a little bigger. So we're going to create a new simple ray path survey. And I'll just draw my line here like this, which I can change the azimuth and the length. I can add more lines, change the line spacing. In this case, I'll leave just one line. I'll keep it fairly simple, and I will increase the station spacing to 200, like that. Then I'm going to drape these source points onto my topography. I'm going to create a 2D grid that we're going to come back to in a little bit. Then I'll choose my reflection surfaces. So that's these ones right here, the pink one and the green one, and my topography. And I'll create that. So what this did, it created two new objects. You'll see here that you have a new curve and a new 2D grid. And we'll start by looking at that curve. So if I select it, you'll see all of the ray paths highlighted in yellow, but I'll just highlight a couple of these. So what this tool is really doing, it's drawing the ray path from the source to every triangle on our surface. And then it is reflected back, and wherever it's reflected on our topography, it's going to draw that point that would be our receiver. And it'll do that for every triangle in our surface. Then this also has a shot ID property, so you'll be able to see what source point does every receiver correspond to. And also the surfaces. So all of these red ones were bounced off this green surface, and all of these purple ones were bounced off this purple surface. So Then looking at the 2D grid really quickly, let's just go on the top view. It has a ray count property. So what this is doing, it's counting the amount of rays in every grid cell. So I'll just show the rays again. So for example, this cell will have 22 rays that, that hit that area. And what that's really doing, it's just giving you an idea of the spread of where you should put your geophones. And another new thing in this version for pro users is that you can export your 2D grids, and you'll be able to export to ER mapper and also GeoTIFF format.
So we're going to start with. And so that model has a rock code that has been prepared by someone, most likely a geologist, and it has been imported and exported through some type of geologic modeling software. So what we want to do is put this information into a UBC-based inversion. So before I do that, though, what I really want is to do a blind inversion. So I don't want to put anything into the inversion yet, just to see what we get. So far everything's been free, and this is where the pro geophysics comes in. So I'm going to use something called GIF tools, which helps us interface with UBC inversions. I'll tell it the type of data my points are, and I'll bring in my model, and I'm just going to invert straight on the model. To create an inversion, I'm just going to go inversion. Today I'm going to use GZ3D, so gravity, but this actually applies to any type of model or UBC code that is available. We need to put the file somewhere, so I'll aptly name it inversion and probably forget where it is later. I'm going to edit options. So I need to set some very specific options here. Mostly, it's going to be my mesh, which is my model, my observed data, which is gravity, and my topography data. I'll do depth weighting. I'm going to turn off the wavelet parameters because it's a pretty small model anyway. I need to set my length scales at roughly 3,200 meters. That's about 4 cells, which is kind of a normal width apart. And that's it. So because the data came in from the gravity data as a UBC gravity data file, it already has an assigned uncertainty. So I'm good to go. So I can actually just write and apply files. I have the option set, things I can do, and I'm just going to go ahead and run the sensitivity and the inversion. While that's running, I'll just briefly show you. I have the metadata that this inversion is running down here. So I have the data I used, the executable name, the length scales, the reference model derivatives, and everything else, and the version and the working directory. So I can always click on these blue links to take me to either the object in the object tree or the actual working directory. So that has been run. So let's go ahead and load the results and just look briefly at what the inversion looks like. When I load the results, it again keeps my metadata. It makes a copy of everything I used for that inversion. So I can always copy the options and rerun it later on. It also grabs the .log file and the .out file. So I always have exactly what I did to create this model. If I simply look at the model, it looks like a blob, which is what we expect from Grav3D. And yeah, so that's what it looks like. We won't go too far because into the data itself. I'm supposed to keep this pretty short, but we have the gravity data we used, the uncertainties that we used, with the predicted data, the misfit, and then the misfit normalized by the error given. And you can see it actually does a decent job of doing it. We have some correlations, but not too bad. So that's a blind inversion, but really we have this geologic information and that's what we want to grab. So the next thing we'll do is we'll add our reference model. So to do that, I'm going to go ahead and just copy the options, and I'll throw it in the same inversion folder. And let me just rename this so I know what I was doing. So that's blind. And this is with a reference model. And so what I'll do is I'll right click, inversion. Now this is where if I want to reproduce the inversion I just had, I just simply write the files and run them. But in this case, I'd like to add the reference model. So I'll go to the inversion, I'll find the reference model object, and I'll find this density prepared. So that's the density that was given to me by the geologist. And then the role in the model objective function. So to begin with, in the model objective function, which describes the model smoothing, we have an m minus m naught, which is where m naught is the reference model. So here it's going to take the difference between the recovered and the reference model into account. So I'll just apply and write files. Inversion, run. I could run just the inversion. I could also just rerun everything in this case. I could run just the inversion because all I've changed is the actual parameters. So I'm adding soft constraints at this point. And so this should take about one iteration. And again, I'm using the reference model as this 1 minus m naught. Let's just take a quick look at that guy first. So this is the reference model, and you can see the data colors here go from minus 0.04 up to 0.26. Great. So the inversion's done. So what I'll do is I'll come here and I'll just load the results. So just like with the first one, I'll get the data, the topography, any predicted data with the misfits. I'll also have the recovered model, and it's going to give me the density prepared because that is the model that I used for the reference model. I'd like to put it on the same data type to make sure that the color stretch is the same. So let me just do that quickly. Great. So this is what we get when we use the inversion with the reference model. Here, this density prepared inside the inversion. So really what it's trying to do is not go away from this model, which is in theory great, but we really started to hit the edges of the model because this reference model was inside the spatial derivative, so inside the x, the y, and the z, not just the smallest model component. So now what we're going to do is we're going to expand this to take out the reference model in the XYZ and only do it in the WS. To do this, I'll just copy the option. And we're going to do the reference model. And this is out of W, X, Y, Z. I can always throw in some more extra comments in here if I want to clarify why I was doing something or what I was doing. I'll edit the options. And here I have this smooth mod diff or smooth mod. So that's the difference here is the smooth mod only has it putting it in the WS, where smooth mod diff has m minus m naught in both the smallest models, the WS and the WXYZ. I apply and write files. And I run. So now I've run 3 inversions, a blind, a reference model, and a model out of the W, X, Y, and Z. And while that's running, I'll go ahead and I'll prepare to use more soft constraints, which would be the weighting functions. So what I'd like to do is create a weighting function between these rock codes down here. To do that, I will select the rock code. I'll build a constraint and go to face weights. And here I'm going to do it between the units. So what I can do is I can take out the reference model, and rather than that, I can say anywhere where the inversion crosses a boundary, a geologic boundary, I can either say make sure those two cells are similar or allow the a sharp contrast. And by allowing a sharp contrast, I would put something less than 1, which is what I'll do here. And so now we have weights. And so when we look, we have cells and then we have faces. So if we wanted to just briefly look at these things, this is what they look like. With this rock code, there we go. And so anywhere the rock code is changed, we have put a face down and made it less than 1. It's done. So let's go ahead and load those results. And for sake of time, let's go ahead and copy those options. So here what I'll do is I'll do just face weights. So I'm going to go ahead and put the reference model back to 0. And I'll just simply add the face weight. So here's where we're going to use the W, X, Y, Z. I'll apply and write, files, hit OK. And run the inversion. And while I'm doing that, let's just take a peek at how this inversion did. So let's just go ahead and view only this guy. And let's change the type one more time to the prepared type. There we go. So you can see how that's changed. So rather than having the real sharp boundaries, because we have taken the reference model and we've gone to just WS, it tries to put a higher density where we had a higher density with the reference model, but it allows it to smooth out a little bit more. And so that's really the difference that we're seeing out of WXYZ and inside WXYZ. So for a long time, we had the reference model inside WXYZ. And so if you gave it a block, it would just give you the block back. But here we can really try to push the densities, susceptibilities, or conductivities towards a reference model, but allow it to fit the data. Great. And so our final inversion's done. So let's bring the face weights in. So load results. And again, I have log files for all of these. So I know I'm flying through here, but we can always go back in and look. And one of the reasons why I have the log files and the model is so I can then compare the two. So here we have GZ 3D. I just need to reassign that. I'll do it to this type just so we can see what it looks like. So here we have softer constraints. So the data type, so the color stretch is on the reference model, but I did not give it the reference model. And that's an important aspect here. What I did do is I gave it the gradient, this rock code gradients on the faces. And you can see where it starts to really try to put breaks inside each specific model unit as it crosses those boundaries. And so there you go. That's been it's been 15 minutes, and I've run 4 inversions, giving soft constraints rather than hard constraints like upper and lower bounds, and different ones. And of course, I can go through and add face weights and reference models, and really try to push the inversion in one area and not another to be able to invert with UBC. but it's a big step up from getting something that that has some geologic information back down to this blind inversion here.